It is Sunday, October 1st, and here at Blue Glow Electronics today, we're going to get into part 5 of the Understanding Vacuum Tube Amplifier Schematics. And as you can see, we're up to episode 5 here on preamps and phono stages. And I'll be honest with the group, I have really struggled with making this video, basically around how deep to go into this topic. There's a lot dealing with preamps and phono stages that can be a slippery slope, and before you know it, you're into some complex math that might exceed a lot of the group here if you haven't had some formal algebra and calculus recently. And so I'm going to keep it kind of high level, but if if you want more or you got questions about specific things, ask me. I'll try to put a video together or answer your questions in the thread. I'm going to try to keep this to a level that I think most people could comprehend. Okay, let's take a look at a high-level block diagram of what a typical hi-fi preamplifier could look like. Keep in mind, this is typical. There's a lot of variations, and I'll talk about those as we go along. But this is a hi-fi preamp. It's got a built-in phono stage and preamplifier stage, as well as volume and tone controls. It's not a lot different than what you would see inside of a guitar amp to amplify and have the tone controls in the preamp section built into an amplifier, or it's not a lot different than what you might see in a microphone preamplifier. And then there are things called integrated amplifiers, so your amplifier stage out here, that might have all of this preamplifier stuff built into your amplifier so that it can do it all. Just one box has both phono preamp stage as well as the amplifier stage. Okay, so let's walk through this block diagram left to right. Typically, a preamplifier, which is identified here in the green, would have multiple source inputs. In other words, multiple RCA jacks on the back of this thing, allowing you to plug multiple things into it. So you might have a phono source, you may have a CD source, you may have auxiliary, you may have tuner, you may have multiple phono sources. You may have one for a moving magnet, you may have one input for moving coil, you might, in an older preamp, you might have one for a ceramic cartridge. So you could have a lot of inputs on the back of a preamp, and typically inside of the preamp you have a selector switch, and this is typically some type of wafer switch that as you turn it, it selects and only allows the one source you select to be amplified throughout the whole amplifier. You wouldn't want to amplify all of these sources because you have a lot of potential to pick up noise in the RCA cables feeding into these things, or just ambient noise in the room, maybe your cell phone syncing, RF, whatnot, getting in. So you want to limit what you're letting in on the input here through the selector switch to be amplified through the amplifier. Okay, so kind of feeding into out of the selector, typically you have, if the preamp has a phono stage, you'll have this kind of combined section here, and it's typically the preamp stage 1, otherwise known as the phono section or phono stage. And in that phono stage, it will also have something in it called the RIAA section, and we'll talk more about that in an upcoming slide. And then it would feed from that into then next, typically maybe your volume control and tone controls for the unit. And then you would come out of that and you would typically go into your preamp stage, otherwise known as your preamp or your line amplifier stage. And so this is designed to amplify the signal again and take it up to a level that could be fed into the amplifier. Well, one thing you might note is if you turn the source to level A here, it would maybe send it through, because it's a phono source, it would send it through the phono stage and then the volume tone controls, then into the preamp stage, the amplifier. But if you selected level B or C, it may totally bypass this preamp stage, it likely would, and go straight from the selector straight up here into this section, into this section, into this section. So a lot of times when you see a preamp design, and if it's got multiple inputs, some of those inputs will bypass the whole first stage altogether, and only the phono stage will go through this first section, and then ultimately you go into your amplifier, and from that you go into your speakers. So let's look at some typical devices and the output levels that they put out. A microphone, if you measured the output of that with an oscilloscope or something, you would see it puts out 1 millivolt to 10 millivolts. Your phono cartridge on your turntable. Most people use a moving magnet cartridge, and they may even not even know that, but most economically priced cartridges, let's say $300 or under, are a moving magnet type, and they put out between 3 and 6 millivolts. That's 3 1,000ths of a volt or 6 1,000ths of a volt. Really small signal. Here's a picture of what we're talking about. If it was a sine wave being put out, you would be measuring the amplitude here of that signal, and that's what we're talking about here. If you jump up into higher end cartridges, which some people would say sound better and are a higher end device, they put out much less, 0.5 millivolts to 1.5 millivolts. So almost 10 times less than a moving magnet cartridge puts out. So if you had a turntable and and it had a moving coil cartridge on it, and you plugged it into a moving, just a regular preamp that was designed for moving magnet, you would be feeding it with about 1/10 of what it's expecting, so the volume would be extremely low. It's very difficult to design a preamplifier to amplify moving coils type voltages without introducing a lot of noise into the amplifier. So sometimes what you'll see is a preamp. Most phono preamps are made for moving magnet, and if you're using a moving coil, a lot of times external to the device, they'll use a little step-up transformer called a SUT, S-U-T, step-up transformer, that's designed to step up the voltage of a moving coil cartridge up to the level of a moving magnet cartridge. And that's not actually amplification, it's voltage transformation. So you trade off current for voltage in that, but we don't really care because the input of a phono stage doesn't require a lot of current to drive it. It's looking for the voltage levels. Then there's this thing called line level. So if we went back to the picture we had up earlier, let me pull it back up. This area here would be considered phono level. So we talked about, these really small 5 millivolts coming in here. Well, now we're starting to talk about this amplifier stage over here. And this is typically you're trying to get things amplified up to line level. So what's coming out right here, going into the amplifier, we're trying to get that to line level. And if you take a look here at what line level is, for consumer devices, which is mostly what we deal with in the home audio space, it is 0.447 volts consumer line level here from here to here. So if you think about it, if you had a moving magnet cartridge going into a phono stage, and then you had to get it amplified up to a level that it could feed your amplifier, which it needs this 0.4 volts here, you've almost got to amplify this thing 100 times to get it there. And we'll talk more about that here in a minute. And then speaker level, typically this is an interesting one. So if you were driving some speakers with 1,000 watts, which is a good bit, but hey, if you were in a concert theater, that's not unheard of. 89.4 volts would be about what it would take to drive an 8 ohm speaker at 1,000 watts. If you remember some basic Ohm's law math and the power formula, power is equal to V squared divided by R, and V is typically an RMS voltage. So if we have 1,000 watts RMS into an 8 ohm speaker, we would use some math here to basically come up to say that is 89.4 volts. You just have to trust me, or you can go do the math if you want. And I kind of did the math over again a couple times. 100 watt amplifier, you'd be driving, if it's an 8 ohm speaker, you would be driving it with about 28.28 volts. And if you were driving at a 10 watt speaker, you'd be at about 8.94 volts. And then a 1 watt would be 2.82 volts. And I use this all the time. I'm looking at an oscilloscope output and I see I've got about 8 volts. I'll say, okay, 8 squared divided by 8 ohms, and that kind of gets you back down to 10. So I thought this was interesting, a little example I did. From a moving coil, way down here, cartridge, into a 10 ohm speaker, okay? The multiplication factor from 0.5 volts all the way up to 8.94 volts, it's 20,000 times that you have to multiply that signal. Because keep in mind, you're going from 0.5, you're going to a half of a thousandth of a volt to almost 9 volts here. It's a 20,000 times multiplication. It's really hard to find an amplifier can do that in one tube stage. So typically you kind of what we call ganging. One tube stage amplifies it some, then another stage amplifies it more, then another stage amplifies it more, so on and so forth until you get to the level you need. Okay, what is this dB stuff? This is where I started really struggling with how deep to go, because this could be an entire series of videos in itself. But you just have to trust me a little bit and roll with this. So the bottom line is, as you start to multiply more and more and more as it relates to voltage, it doesn't necessarily translate into how you hear or perceive that voltage gain. In other words, at some point, you know, a 20,000 voltage gain doesn't sound much louder than a 10,000 voltage gain, or much louder than a 5,000 times voltage gain. So there's this whole concept of using, if you go back to some basic algebra, a logarithmic scale where this kind of goes 1 through 2, 3, 4, 5, 6, 7, 8, 9, 10, and they get closer together as you go. And then when you get here, it kind of goes 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, then 100, 200, 300. You kind of get the idea, but it's a way of mapping something on a logarithmic scale that then maps better back to how this gain, either increased or decreased, actually gets perceived. So if you have something, and it's all about a reference point. So let's just say we have something and it's playing at a certain volume, just a really low volume, but you can hear it. If you said we were either going to increase or decrease the gain 0 dBs, well, that would be the same as multiplying it by 1.0. Well, if your little signal was 1 volt and you multiply it times 1, it's still 1 volt. So 0 dB is no change. But if you multiplied that 1 volt times 1.414, that's actually considered a 3 dB gain. If you multiply it times 2, it's a 6 dB gain. If you multiply it times 3.1, it's a 10 dB gain. If you multiply it times 10, it's a 20 dB gain. So this scale is not linear, it's logarithmic. The same way as if you reduce the volume on something minus 3 dBs, well, it would actually be at 0.707 of the original voltage. Why on earth the world does not talk in terms of voltage? I struggle with it, but I get it. I get why they do. From an electrical engineer standpoint, somebody working on equipment, you will always be working in voltages. If you're a sound producer, somebody working with professional audio equipment, whatnot, things always get translated into dBs, decibels. It's a measure of sound pressure level into the ear, basically, and so that it's an easier way of determining variation or change in voltage or what you're perceiving as the voltage change or amplification or de-amplification. All right, so dBs can be represented different ways. There's such thing here as called a dBV, which is kind of comparing back to 1 volt RMS. So if you say this thing is 3 dBV, well then it's, if you go back to the previous slide and bring that up, right, it would be at 1.414 times the original 1 volt, if that makes sense. So 1.41 volts. If you're measuring dBUs, dB units, it's compared to 0.775 RMS. If you're measuring dBm, it's representing it compared to 1 milliwatt of power. So it actually turns into a power measurement. And this is where This could turn into a whole video series, so you may just want to go out and find a couple videos on dB measurements, and it probably help you out some, because I don't think I can go into that depth in this video. And then there's something called dB-SPL, which is sound pressure level. This is a great little table here. I thought it showed, you know, if you're just walking around outside, the noise of the wind blowing, the noise of the leaves rustling, it's about 20 dB above just absolute quiet. People in a library whispering, talking, that might be 30 dBs. You know, a typical living room might be 40, a traffic light, average home, about 50. Air conditioning unit, people talking, 60 dB. You can kind of see here as we go up a firecracker, 100 dB. A rock concert, 110 dB. A jet engine, 140. A rocket launch, 180. Well, what you might realize if you were doing this on a voltage scale is the difference between leaves rustling and a jet engine might be 1,000,000 times higher, but on a dB scale it's only 140 higher. So it's a relative way of reading things using a logarithmic form. So a lot of times you'll see these types of charts as it relates to either a preamplifier or an amplifier, and this is something known as a frequency response plot. And I use a piece of software from Pete Millett along with my HP8903 to make these plots, and there's other ways of doing that as well. But what it does is it takes a frequency plot and it goes from, say, 5 hertz all the way up, or 0 hertz all the way up to 20 or 30 kilohertz, and it kind of plots the output of your amplifier against that. And typically you'll see here that this thing is fairly flat here all the way here from, I would say that's around 18 or so hertz, all the way up here to about right here, about 18 kilohertz right here is where this thing you could say is fairly flat. So the way you talk about a reduction in that is measured in these dBVs, decibels voltage. So if you'll notice, if down here at 5 hertz, this thing's down about maybe 1.5 or so dBV. And if you'll notice, this thing stays pretty solid all the way up here till a little after 20 kilohertz. Then it drops off very quickly. But it's a way of representing how your amplifier amplifies at a certain frequency and how far down in dBs that thing would be measured. And one thing you typically do if you want to give a quote on the bandwidth of an amplifier, that's typically measured at -3 dB. So the bandwidth of this amplifier would be all the way from 0 all the way up here to about 25 kilohertz that this thing stays above the -3 dB mark. So pretty solid amplifier here. Okay, so another slippery slope here, different topic, RIAA equalization. And this is known as, I'll read it here to you and then I'll try to explain it. It is a form of pre-emphasis on recording and de-emphasis on playback, with the net result at the end of the day being a flat frequency response. So when you actually have a record cut, or what they call mastered, and they use a lathe to actually cut your acetate, they actually do something. They use an RIAA filter that actually on recording de-emphasizes the bass notes, the lower frequency notes, and they emphasize the higher notes. And the reason they do that is bass notes on a vinyl record take up more space. In other words, the grooves have to be wider, they have to be deeper, because you've got this larger movement of the actual needle at that point. So if you de-emphasize this on your recording, what that does is it actually allows you to put the grooves closer together on the record, which allows you to get more time or minutes onto a given recording. And then by emphasizing the highs here, you know, it helps to keep from having shallow cuts or shallow grooves in the record for the highs. Gets rid of some of the hiss and noise. And then what happens is, so if you play a record back into a preamp that doesn't have an RIAA amplifier stage in it, then your record sounds pretty horrible. It sounds like it has no bass to it. Sounds like the highs are cutting you in half. And so what you do when you play this thing into the phono stage of an amplifier, typically it has a couple components to it that are designed to kind of de-emphasize then and basically do the exact inverse of what they did when they were mastering this thing. So the net result, if you add those two together, is you end up with a flat frequency response going through the rest of your amplifier. And so you could almost think of it as you're taking away something when you're recording it, and then when you're playing it back, you're adding it back in. Or in the case of the highs, when you're recording it, you're emphasizing those more, and then when you're playing it back, you're de-emphasizing those a little bit. And it'll tell you down here at the bottom, RIAA is not a simple low-pass filter, and that's where I got trumped up on should I go deep into this or not, because this could be an entire video series on itself around low-pass filters, high-pass filters. But go look up low pass filter and just see if you can find you a video on what that is. Maybe it'll help explain some. But this thing actually has a pretty complex, what's called a complex filter. It has multiple notch points. In other words, it has 50 hertz or poles, they call them. It has a 50 hertz pole, a 500 hertz pole, and a 21.22 hertz pole. So the 50 hertz pole's somewhere right around in here. Then you've got another pole here at the 500 hertz, which is right in here. And then you've got another pole up around 2120 hertz. In other words, if you were bending this thing, you notice the bend here, then it starts bending back that way, then it starts bending back this way. These are where the bends actually take place. And, you know, you've probably played around with this before in your life with an equalizer. If you pull down these over here, you're basically de-emphasizing the bass on your sound, and if you push these up here, you know, your highs get higher. You're just kind of doing the exact opposite of that when you're playing this thing back in. You're then saying, whoa, let me boost these highs a little bit, lows a little bit, and decrease the highs, and then this thing sounds just the way it was before it was ever put on the vinyl lathe. All right, another one of those slippery slopes, but notice everything we're talking about is in dB now. It's just a relative way to measure, and if you can get you a chart and figure out that minus 90 dB is, you know, X amount of voltage delta between this and this. But if your amplifier or preamplifier can handle this entire dynamic range here of signal, somewhere introduced into your amplifier, either via the power supply, maybe just noise on the line, the RCA cable feeding into your amplifier, maybe the resistors and components inside your amplifier are producing some noise themselves. There's always this undesirable amount of noise that exists that you're trying to get rid of. And in a really good preamplifier, you're typically, it kind of shows here, 90 dB or more down. You'll talk of it in terms of down from the original signal. So in other words, if your whole signal is 96 dB, you would want to be somewhere around 90 dB down from that. In other words, just a small fraction of your overall signal should be noise. And this is important, very important in a preamp, because let me pull back up for you this. If this little part of the amplifier right here has noise in it, that noise is going to get amplified here, all along the way. So you want to introduce as little noise as you can in your preamplifier, because whatever noise gets introduced is going to get amplified by your amplifier. All right, and so you can see here typical noise sources. Maybe a misaligned phono cart. That thing's rubbing up against the wall all the time, and you're getting your normal vocals and music, but you're also getting some noise that you shouldn't get because your cart's not aligned properly. Maybe your turntable motor itself has some vibration to it. That can be a noise source. Your RF cable, preamp power supply, the tube filaments in your amplifiers can cause some hum. Transformers, if you align transformers the wrong way and they're interacting with each other, you can get some hum. Improper grounding or grounding loops, maybe the power supply in your amplifier, or just a poor design. Maybe you're trying to do too much amplification in that first stage and you're picking up a lot of stuff you shouldn't and passing it along. So all these things can play a role. But keep in mind, this whole thing is about a ratio. The amount of signal you have overall to the amount of noise that you have, and you want to keep that figure as low as possible, but the way it gets measured, you want the number to be as high as possible because you're saying 96 dB down from your overall signal. I know some of what I've talked about is getting a little bit technical, and there's a lot more to it than what I'm able to get into here in a short video. So if you got questions about dB, go out and search and find some videos out there and watch on that topic. I know there's some good ones out there. Same if you got questions about signal to noise ratio, there's some good videos out there on that. I'm going to get into one more topic here that's a really steep slope, slippery slope, and that's about impedance. So resistance is the it's the resistance to the flow of current in a DC at DC. Reactance, or otherwise known as impedance, is how current gets affected at an AC, in other words, an audio signal or a AC signal. And frequency is a contributor to that. So I'm not going to go into this. I just put the math here to show you why I'm not going into it. So Z, otherwise known as a complex impedance, otherwise known as a complex, it's made up of both what's considered inductive reactance and capacitive reactance. Both those two are kind of combined here, squared. And then you take the square of your resistance, and the square root of all that is your overall impedance calculator. But then you got to be able to figure out, well, what is this reactance inductive here. So you kind of got your formula. XL is equal to 2 pi f. And this is where frequency comes into play, times the inductance, and the same here with capacitance, a complex formula. Bottom line, you can see why I'm staying away from getting into the deep understanding of what impedance is. But I'm going to give you some guidelines here that'll hopefully help you understand it at a layman's kind of level. So typically, you want a low impedance source, okay, connected to a high impedance device. So we'll talk about that here in a little bit more in a minute. But let's just say you want a low impedance, let's just say phono cartridge connected to a high impedance preamp, or a low impedance preamp connected to a high impedance amplifier for maximum voltage transfer. And I notice I said voltage. The rule of thumb, you want a preamp output impedance to be at least 10 to 20 times less than the input impedance of the next stage. So if your preamp output impedance was, say, 10K ohms, you would want your input impedance on your amplifier to be at least 100K. On the contrary, if you want to match the maximum power transfer, which is what you're wanting to do between your output transformer and your speaker, you actually want the impedances to match. So you would want an 8 ohm output tap on your output transformer to match up to an 8 ohm speaker. But when you're talking about sources for preamps, phono stages, amplifiers, you want this 10 to 20 times multiplier there. And typically the input impedance of a tube device, so the tube first part of a phono stage or a preamp stage is typically set by the grid resistor of the first stage. That says state, but first stage. And or maybe that resistor is combined with some type of potentiometer as part of the volume setup. But that's typically what defines that input impedance. So these down here are just some typical values. A moving coil phono cart, about a 10 ohm output impedance. A moving magnet, between 1K and 2K output impedance. Ceramic cartridge, 100K to 1 meg output impedance. That's why if you plug a ceramic cartridge into a moving magnet preamp or phono stage, it doesn't sound so good. You have a horrible impedance mismatch there. A phono stage, so if you're going from a 10 ohm output on a phono cart into a phono stage, you'll notice on average about 100 ohms input, which is about 10 times that. Moving magnets, typically 47K is the input impedance, so it's like more like 20 to 40 times here. And you typically on the output of a phono stage, you'll typically see anywhere from 10 to 100K output impedance. And then feeding into a preamp, 100K input impedance. Then you'll see typically 10 ohm to 1K output impedance, which would then feed into an amplifier that has 10K to 100K input impedance. Then on the output, you'd typically see 4 to 16 ohms, which at that point you're trying to do a match to your speakers, 4, 8, or 16 ohms. So you can typically see from the cart to the phono stage, there's a 10x, sometimes 20 or more multiplier. When you go from your phono stage to the preamp, there's typically a 10K match there. When you go from your preamp to your amplifiers here from this 10K, 1K, you get anywhere from 10 to 100 times here. But then on your speaker outputs, you actually want to match that up. And I don't know how to explain this much simpler without getting into the math up here. And so that's where I'm just going to kind of stop, and maybe you can find some other videos out here that talk about impedance matching and you know how they're explained. But it's some of these topics, not every topic in electronics can be explained in such a simple way that anybody can understand it without getting into the mathematics of it, unfortunately. And this is kind of one of those topics. Okay, this is just a circuit example 10, a phono stage. And keep in mind, this phono stage could be a standalone box by itself. You see a lot of little units you can buy out there that's nothing but the phono stage. Or it may be integrated into a preamp. So you got the phono stage and the preamp all together in one. Or it may be, like I talked about earlier, an integrated amp that has all of these built into one. But let's take a look here. This is a kind of an older circuit here, but it has both a magnetic input, in other words, moving magnet, and it has a ceramic input. Remember, it had a much higher input impedance. So if you feed into the magnetic input, it kind of bypasses here this whole section and comes over here and fits right into the grid of this tube here, right? But if you fed into the ceramic input, well then R1, R2, and C1 all come into play at that point in time. And R1 and R2 here, these become kind of the loading of this ceramic thing. And if you'll notice, remember we talked about, you know, this could be all the way up from 10K, 100K to 1 meg. And so this 2.2 meg here helps kind of be that 10 times multiplier that you need. And C1 here is a little bit of a tone compensation for this overall ceramic input. You then get here into R3, which is just your grid resistor here, feeding into the grid of the first stage of this 7025, otherwise known as a 12AX7, a nice 12AX7. So then you would kind of feed out of that over here into the to the next circuit. But coming off the cathode here of this tube, you would have the cathode bypass resistor here, R4, and it is paralleled with a 50 microfarad capacitor here, which is the cathode bypass capacitor. What this is kind of designed to do here, this cathode bypass capacitor, it kind of reduces what is known as degenerative feedback. So think about it. The cathode here has a DC voltage sitting on it, and this resistor here helps kind of set that level. But it also has AC sitting on it right here that's kind of came through this tube. And what this does is this provides a short to ground for that AC, so that you don't end up with a variation in voltage across this resistor from your AC, which is then kind of creates a feedback loop here between this cathode and the grid, and kind of causes a degenerative effect. So actually putting this capacitor here gives a short to ground for your AC, and kind of gets the AC off of this cathode. And what that does is it increases the gain of this stage overall. So coming off of the plate here, typically you see something that goes up with a resistor here, and you have your B plus up here. Well, they drew it a little different in the schematic. If you'll notice, they came over here and they drew it this way, but it really doesn't matter. It's the same thing. They're telling you this is your B plus of 130 volts. You have your plate resistor here, or your plate load resistor. And if you'll notice, coming off of your plate here, you're feeding into the next part of the second. Let me see if you can guess what this is. If you guess coupling capacitor, you're correct. You're keeping this 130 volts off of the next stage here. Now this is where it gets interesting. If you'll notice this, there's 3 sets of resistors and capacitors kind of put together here, okay? And these are high pass and low pass filters being built. Some of these in series, as you can see, some of these in parallel here, back in series. That is creating those poles that we talked about earlier, the 25 hertz, the 500 hertz, and the 2250 hertz. That's what this is creating. This is your RIAA stage. You're coming out of it, then you've got the R10 here, which is your grid leak resistor on this. Then you kind of you've got your cathode resistor here on this one. Then you kind of feed out the other. Keep in mind, this is the second side of this bottle, the other half of the 7025. You come out of it, and you're feeding to the output through, yes, you're right, another coupling capacitor. And let's guess what this is. This right here, it is the plate load resistor going to your B plus or high tension voltage there. But there's also another feed here. What's this? It comes back over here, feeds through a capacitor, a resistor and a capacitor, and it feeds back into your circuit here to come back around through the RIAA. What this is a feedback loop. So it's your negative feedback loop for this circuit. And then you're coming out through this coupling capacitor into a 100K ohm resistor here, which actually R13 here really helps set the output load on this thing. So of about 100K here on this phono stage. Okay, I'm not going to walk you through this whole schematic, but I thought I would show you. This is a typical, this is actually a Conrad Johnson preamp that I went and found the schematic for. And what you've got here is you've got a tape input, a tuner input, a phono input. And if you'll notice, if you feed into the tuner, watch what this wire does. It comes over here, skips here, the switch feeds it. It comes from here straight down in and feeds the preamp. In other words, if you flip the switch here in your selector switch to tuner, you completely bypass this blue box altogether. Interestingly, if you feed in here on tape and you come over and you hit the switch, it can take you straight over here and on the output, so you kind of bypass both sections of this thing, if this was part of your tape loop. But yeah, so if you fed in phono here, you would come in just like this in the grid of this capacitor tube, feed over coupling capacitor into the grid of this one, come over here. Well, guess what this whole section is right here? If you guessed RIAA section, you are correct. So you kind of feed through the RIAA section. You come out of that, then you feed over here through a coupling capacitor into the first stage of this tube, which then does amplification, feeds you into the second stage of this tube, then ultimately the output here to your amplifier. But notice what else there is here. There's a little bit of a tap off the output that comes around. Here's a resistor and a capacitor, feeds back over here, feeds into the cathode of this tube. It's a form of global feedback in this preamp stage right here, this whole little section here feeding back over. So all in all, a fairly simple schematic, but as you can see, you just got to start breaking them down. So if you threw up a schematic here of, say, a Fisher 400, 500, there's a lot of sections to that thing because you've also got the AM, FM sections. But if you take each section and break it down, draw a little box around it, figure out what it does, figure out how it feeds to the next section, kind of break it down, put a box around it, you'll kind of eat the elephant one bite at a time, and you'll start to understand how these things work. Keep in mind, we're going here from a multiplication here, a 0.5 millivolt signal maybe here, or 5 millivolt if it's moving magnet on this phono, getting multiplied maybe 100 times here, and then maybe 100 times here. Well, if you kind of do the math on 100 times 100, right, you've already done an amplification of 10,000 at that point. And remember, I told you to go from amplification all the way from this all the way to the output of your amplifier at 10 watts. You might need 20,000. So maybe the amplification on this is 10. Maybe the amplification on this is 20. Then maybe you get over here, it's another 50 or 100. You kind of get the point. You don't want to do it all in one tube. One tube couldn't do it, but two, it would have to handle a lot, and doing so could pick up a lot of noise. So you kind of want a well-designed multi-stage amplifier. You'll see a lot of amplifiers, the Marantz 7, Dynaco Paz 3, and others. You actually have 3 tubes in your phono stage and 3 tube sections in your preamp. Also, that you're not trying to do too much in any one stage. So hopefully you learned a little bit. There was a lot more I could go into: buffer stages, cathode followers, mu followers, different pieces, and maybe we'll do some videos later on more in depth on preamps. But I just wanted to kind of give a high level overview at this point. Thanks for watching, everybody. If you got questions, ask. I'm sure you will. It's a big topic. I tell you, designing and making good preamps, phono stages, is much more complex than designing amplifiers because of all these factors that you have at play here. Stay tuned. We've got more coming.